Hi, Jason. Hello. How are you? How's everybody doing? I'm good, thank you. How are you? Okay, so we're going to do final review today. I'll give everybody a few minutes to join. We'll start at 6, okay? So check out Canvas. Okay. Hi, everyone. Yeah, it is near the end of the semester. All the classes are finalizing, so I understand. Okay. Oh, thank you for pointing that out. Let me fix the due date. I thought maybe I changed CIS-11 and I forgot to change yours. You are correct. Let me fix that, okay? I don't know why when it rolled the dates, it's supposed to apply all the dates that I specify, but okay, so we'll make it to the 30th. We're gonna have it available today. Let me change the availability date. Okay, let's save that.
Part 1's due date is set to last year.
Canva's supposed to apply all the due dates accordingly, but it's not. So let me fix that. Thank you, Ryan. Okay, I'm gonna save that real quick for this third part. Let me go part 1. I should have triple checked it. Okay, so May 2021. Okay. Give me 1 second and we'll get started, okay? It's not letting you see some stuff because the date is not applied. And then availability. Okay, let me save that, and it should take effect now. Sorry about that. Okay, so I think we got everything changed and everything's good to go. So I like to start with part one, and we'll see how far we're gonna go. If I can't cover everything today, we can meet again on next week to be able to cover that, because I know that I want to give you time to work on your project as well. So I'm available Thursday in case you have questions, so you can come in to Zoom and ask questions if you need to. I looked at the group assignments or sign up sheet on Google this morning, and it seems like there's still some of you that need to get organized and work with the group. So make sure, I know that some of you put your name on there. So if you're looking for a group, look for people who had signed up and then maybe possibly join them. If you need me to help you reach out to the people in your group because of lack of communication, please let me know. Okay. So let's get to screen share real quick. Okay, so I like to go over part one first, and then we'll go as far as we can today. So this is going to be chapter 1 through 6, and also final exam is going to be open the first day of the week. I want to show you that I already turned on the. I already turned on. Actually, I didn't for you guys. So I will turn on the lockdown browser information, and then it's going to be open on the 7th of June, and it's going to go until the Thursday, which is the 10th, for this class. So for the other classes, it's going to open on Monday and close on Wednesday. So for your class, I'm going to open it until the 10th of June. So make sure that you dedicate time to do it. I allocate 2 hours for the final. With 50 questions. If you need more than the 2 hours, make sure that you reach out to me beforehand so I can assign your name to more than 2 hours because of accessibility. So make sure that you let me know. Password will be used for the final exam, and I will send out an announcement that morning on Monday, which is the 7th. You will find the password on announcement. Also, I will include it in the final module, so that way you're not confused and try to look for the password when you're trying to get started, okay? I usually allow 2 tries for the final exam, and I will do that this time. It's multiple choice, so if you're not happy with your score the first time, you can retake it. And so that way, your final score is going to be the highest score, and that will be by the due date. So if you don't take the final by the 10th, I do not allow late final unless there's dire circumstance and you need to contact me, because the grades needs to go up and things need to be tied up and sent through WebAdvisor. And sometime when a lot of faculty are on there, WebAdvisor act a little funny. So want to make sure everything is good to go for you by the next week. So I got to grade your project as well. Project is due on the 10th. Make sure that you upload everything, and it needs to be individually submitted. So don't rely on your team members to turn stuff in. Make sure that you have all the parts and put them together and submit those. Okay. All right. So final review part one. The first part, the first chapter, we cover uh, the hexadecimal, binary, and decimal systems, very similar to the CIS-11 courses if you have those with me. So we need to know how to do conversion. Now on the final exam, I enable the scientific calculator on lockdown browser, but you will not have the programmer mode. So make sure that you know how to do the conversion. So on the final, you will get similar questions to these. So question 1, it asks you, what is the binary equivalence of decimal 205? And so you can use the table like what we did before, but if you wanted to do that manually, starting with the right most digit, which is going to be your least significant bit, and you can write out your scale 2, 4, 6, 8, and so on. It's multiple of 2 starting with 1, so on the right. And this is an odd number in decimal, 205, so the least significant bit is going to be on. So that's going to be a 1, next to it is the 2, 4, 6, 8, and so on. So make sure that we know how to do the conversion, and 205 should be equal to 11001101. And similar to your quiz, it's going to tell you in the question that the answer should be expressed in a byte, right? Or a word, or a double word, or a quad word, and so on. So in the case where you get a negative value, you just make sure that it's going to be sign extended for all the bits. That's going to fill up that storage size, okay? So in this one, we converted 205 to binary. And then for number 2, we wanted to convert hexadecimal for E to C to binary. And that's very easy because each hexadecimal is going to equal to 4 bits. So we can start with the 4, and 4, we can convert that to binary. So 0, 0, 1, because it's turned on at the 4 equivalents, and then 0, right? So that's going to be for the 4. And then E, we know that E is going to be equal to 14 in decimal. So from decimal, we can convert that to binary. That will be 0, 1, 1, 1, because 2 plus 8, right? And then, so 2, 4, and 8 is going to give you 14. Then on the next one, it's 2. So 0 through 9 in hexadecimal is equal to 0 through 9 in decimal. So the 2 is going to give you these 0, 1, 0, 0, because the bit at the 2 is turned on. And then for C, we know that C is equal to 12 in decimal. So that will be 4 and 8. So 0, 0, 1, 1. So when we put it all together, right, we bring down the 4 equivalent in binary, we bring down the E equivalent in binary, and so on. So you just combine all of them together and you would have your binary. Okay. Any question with 1 and 2? All right. For number 3, we need to know how to do 2's complement. And so you start with the given hexadecimal 8A2, and that's base 16. So it's a hexadecimal. And we wanted to express our answer in a word size. So that's going to be 16-bit. And we wanted to make sure that it's going to be hexadecimal in our answer. So the first thing that we can do is the easiest way to do is to convert it to binary. Okay. Or that we went over where we would subtract 16. But in this one, if we convert it to binary, we would start with the 8. That's the leftmost digit, which is going to be the most significant digit. So here is the 8. We convert it to binary with the 4 bits. My internet connection is low, so let me turn off my video there. Okay, so 4 bits, so that's going to be equal to 8. Then A is equal to 10. And so in binary, 10 decimal is 1010. Then on the next digit, it's going to be 2. So 2 would be 0010. So when we put it all together, we would have this binary. Then the ones complement, we're going to not it. So we're going to flip the bits. So the 1 in the front here becomes the 0 next to it becomes 1, and so on. So for the ones complement, we would have 0, 1, 1, 1, 0, 1, 0, 1, 1, 1, 0, 1. We're not done. So on the test, right, you're going to see the question for the twos complement. Do not stop at the ones complement and select that as your answer. We got to add the 1 to make it the twos complement. So we simply going to add the 1, and remember that when we add the 1 to the back here, that's going to carry. So it's going to become 0 with the carry 1, right? 1 plus 0 is going to give you a 1, and then the rest just drop down. Okay, so at the twos complement, this is what you have. Okay, now when we need to convert it back to hexadecimal, notice that I leave it with the 4 bits so I can convert it back easily. Okay, so in the front, you would have 0, 1, 1, 1. That's going to be 7. Okay, and then next to it, 0, 1, 0, 1. That's going to be 5. Okay, because 1 plus 4 gives you 5. And then next to it, 1, 1, 1, 0. That's going to give you 14, which is going to be equal to E. And remember that when we go from this into its twos complement, really we're going, if we start with an unsigned value, we're going to have to be signed in our answer. And here I put the note that F signifies the negative value or sign value. Okay, so you need to have the F in the front, and then you bring down the 7, the 5, and the E, and that will be your answer. Okay, so don't forget about the sign digit, which is F for hexadecimal. Okay. Make sure we know how to do twos complement. Do you have any question for me for number 3? Okay. So now on the next one, number 4, we need to determine the twos complement for decimal 2 or 811. Provide answer in binary. So first thing first, we need to convert 811 to binary, right? We can use the multiple of 2 scale, and we can use the subtraction method, or if you want to use the division method, whichever is easy for you. You don't have to show the work on the final, so you just have to be able to determine the right answer. So here I did it with the subtraction method. So here is my binary value that's going to be representing 811 in decimal. And then I flip the bits or not it. So the 0 in the front becomes the 1 next to it becomes the 0, and so on. And then that will give me the ones complement. Then I would add the 1 to that to get me the twos complement. So this is my final answer. Okay. And in this one, we simply express it 2, 4, 6, 8, 10, 12. Notice that it's 12 bits. And if the question asks you to fit it into the word size, right, we need to fill in the 4 bits in the front, and that needs to be sign extended. Okay, so make sure that we remember to do that. Any question with twos complement, number 4? All right, no question. Okay, so pretty easy stuff. We need to know how to do binary arithmetic, right? And in number 5, we need to add. So remember the addition rule. I put down here that the important one is the one with the carry. And when you use the carry, recall that in the first week we talked about how we would handle the the carry with the top number, get the result. When we add it, then take that result and add it to the lower number when we line them up. Okay, like for example, this one, like 1 plus 1, right? That's going to give you a 0 with the carry, and then we bring the carry to and add it with the top number, and then have the result, take that result and add it with the lower number. So this would be my output. And I didn't space it out, so it didn't line up exactly, but make sure that we go back and review the addition rule for binary. And then also know how to do subtraction. Okay. And for the final review, if you just put the answer, that's fine. You don't have to show the work. If you don't want to show the work, that's okay. I just want to make sure you know how to do it. So make sure that we remember the subtraction rule as well. So 1 minus 1, you get a 0. 1 subtract 0, right? You get a 1, and so on. So when you, in the case where you need to borrow, right, when you have a 0, subtract 1, right? Recall that. So in that case, again, just like what we talked about before, we're going to handle it in the next column, and then make sure that you use 2 number at a time. So the borrow with the top number, get the result after you subtract it, take that result and then subtract the lower number in that column, and then you get the final result for the answer. Okay. And just double check it and make sure that you apply the rule accordingly. Now in the computer, right, when we use the calculator, it doesn't care about the 0 in the front. So you would then, you know, it omits it. But you know, if it's easy for you, you can write it out. Okay, so make sure we know how to subtract. Along with that, for number 7, we need to know how to use the operators like or, and not. Okay. So anytime that you or a 1, when the 1 is in the mix with the or rule, you get a 1. Okay. So 1 or 0, you get a 1, 0 or 1, you get a 1, and so on. 0 or 0, you get a 0. So make sure that we know how to find the result with the operator. Any question with these? Okay. Then for question 8, we need to know how to use NAND, which is and then we not it. So here I show my work. So first I wanted to AND them. And anytime that you AND a 0, you get a 0, right? Like think about the if statement. If you have this and the other one, they both have to be true in order to execute. So anytime that it's false, right, it's going to kick it over to the else, or it's not going to execute. It's not going to execute the if. So then we have the and 1 and 0, we get a 0, right? 1 and 1, we get a 1, and so on. So we got the and. We're not done for the NAND. So after we got the and, we're going to not it. So we're going to flip the bits. So the 0 becomes the 1 and the 1 becomes the 0. Okay, because it's not and. So we and it first and then we not it. Okay, so make sure that we know how to do NAND, NOR. Okay. Any question with 8? Okay, then you got some of the questions.
Wouldn't word size be 16 bits?
Yes. When it asks you to express in the word size, a word for us is 16-bit, right? The architecture that we use, a word is 16-bit. And for, you know, Intel, Microsoft ones too, okay? Only when you deal with some of the later ARM, okay, programming language in the later architecture where you would have a word is 32. Okay. Okay. So we saw some of these questions on the first quiz already, right? So number 9, what type of architecture under ISA classification directly uses memory instead of the register file to hold data and instruction, and that will be CIS, complex instruction set. And that type of architecture directly accesses memory. For LC3, for this class, we use RISC, and the majority of the ARM are the later architecture that you use in smartphones, tablets, and so on, they're RISC, right? And it uses ARM. Okay, so for number 10, which architecture requires more complex hardware to implement instructions, which generally register to register operations, right? Remember how in our instructions we do like R1, R2, R2, right? Add R1, R2, R1, so on. So that will be your reduced instruction set. It relies heavily on the hardware. And so therefore you would see the instruction sets are more simple, okay? And it's heavily used in the industry because it's while they design it, they build it, it's easy to develop. Okay, so we use RISC in this class if you haven't gotten that since the beginning. So CIS for 9 and RISC for 10. Know the difference. For question 11, true or false? Directive is built upon discrete statements or instructions that requires particular registers for arithmetic, addressing, or control functions. Memory allocations or offsets, addressing mode used to interpret the operands. That's false. And really, it's not directive, it's machine language is built upon discrete statements and or instructions. Machine language, okay? And at the low level, that's what assembly is all about, right? It's about, writing instructions at the machine level. In the earlier chapters, they touch on p-type, and we talked a little bit about transistors, right? So for number 12, it asks you about what type of MOS or MOS transistors pulls voltage up when receives 0 inputs, and that will be your p-type transistors. P-type transistor, it pulls the voltage up for the input is 0. The way that I remember this when I first learned it is I always think about p-type as in positive charge. So it would pull your voltage up. When it receives the 0, it's gonna pull it up to positive charge. So it pulls the voltage up higher. So that's how I remembered it. But however you would be able to use it and remember this. So p-type is gonna pull when it receives a 0. So when you have an input of a 0, right, with the MOS transistors, p-type is going to give you higher voltage. For 13, what type of sequential circuit systems coordinates signals and control data movement? And that will be your state machine. State machine coordinates signals and data movement. For number 14, fill in the blank. A circuit that charges a code into a set of signal is known as a decoder, right? In the earlier chapter, I think week 2, we touched on the transistors and we talked a little bit about state machines, okay? So for 14, decoder. For 15, what type of circuits is used to trigger transitions from one state to another state in the state machine? And that's your clock circuit. Okay, clock circuit. It triggers the transition from one state to another state. Any question with 12 through 15? Okay, so here, this kind of lead us into the instructions on how it would set up which bits are dedicated for, you know, instructions for offsets, for registers, and so on. So in the word, which is 16 bits, the way that we denote this is gonna be from the left to right bits, right? So the left bits here is gonna be 16. Okay. So, or I'm sorry, 15, because it's going to be from 0. So we're going to have, when we look at the highlight, we're going to go 15. We're going to count it backwards: 14, 13, 12, and 11. So for the highlighted bits, that will be 15 through 11. We would put those in the square bracket, and the values, the binary value would be this. Okay, so make sure that we know how to read the notation for the bits, the bit notation. For 17, fill in the blank. A transistor that performs the basic logical functions and considered to be the fundamental building blocks of the digital integrated circuits is known as logic gates. Okay, and I showed you some picture on what that would look like, or they could be very small, or they could be physically the size of like maybe a small pinky. I've worked with logic gates with Arduino before, right? But inside your processor, you would have logic gates. They are components of transistor that perform your logical functions. And when we look at assembly, right, you see that a lot of times we add, and then we would use logical operators. So at the machine at the lower level, you see some of that, and it require logic gates. So they are the fundamental building blocks for the digital integrated circuit. So when you go into engineering and you would take, digital integrated circuit classes, right, they would emphasize a little bit more about design, circuitry, and all of that. Okay. So the blank here, that will be logic gates. They are the components of your transistor. Okay, 18, the differences between combinational and sequential circuits. Okay, so combinational circuits, it provides the same output given the set of inputs, which makes it stateless. So remember, the combination is stateless. Sequential circuits, it stores information which contains its state of output. So it is stateful. So sequential is stateful and combination is stateless. Okay. So going back to those modules, you have access to the presentations that were provided and also your notes. So you can go back and visit the notes, the content, and even I posted the video, so you can come back to that to review. Any question with 17, 18? Let me move this down a little bit so you can see the answer for that one still. Okay, because it's dropping to the next page. All right, so no logic gate diagram. This is a must for this class. Okay, and even my other class, I want to make sure I train them. So when you look at the logic gates, right, which of the following logic gates represent not and or nan. Okay. Remember that when we talked about the logic gate diagram, the the way that I remember this, the way I learned it is the and, right, looks like the D, okay? And when you have a bubble, that's the not. So we and it and then we not it, right? Remember earlier? So B is going to be the not and, okay? A is the nor, okay? So when it looks like the arrow, that's an or, and then the bubble, that's going to be your not. So or not, that's the nor. So A is not nan. Okay. B is nan. And then if you look at the other options, C is and, right? Without the bubble, it's just and. So that looks like the D shape. So that's and for C. Okay. So for number 19, we would select option B. Okay, so I wrote it out for you so you can see the difference. Any question for logic gate diagram? Okay, no question. So for 20, in a combinational circuit of a processor, which component permits input and output selection? And that's your MUX, multiplexer. Multiplexer. Okay. Before, when I taught this class, I shared this with you before, I require lab 2 would be the students. They have to draw the diagram using a simulator. You can find a lot of them online now. Before there was not, so we would use an install program that would do it. When you get in, if some of you go into more engineering courses or electronic engineering mainly, they would have to know how to draw digital circuits. Okay. 21. Which assembly operation writes the value to memory location? And that will be store. It writes the value to the memory location. Okay. And in LC3, that's a little different, right? So when we do the storage in LC3, we have to do what? We have to save and restore, right? The way that we save it is we gotta get the register to move it. We would load it and then we would unload it. Okay. So you would use LD or LDI, or if you do it with registers to register, like the example in the book, that will be LDR, right? And then you would store. So when you store, you write it to the memory. Okay. So when you load it, you got to store it back, like what I always say. So it's ST, STI, STR. Okay, store. Let me type that here. Okay, so for 22, in a processor, which component is considered as a small temporary storage of the processing unit? And we would use registers. And in LC3, we use R0 through R7. Okay. 23, in addressing mode, where are the operand, when can an operand be found? Okay, in 3 areas, either in memory or in register or as part of the instructions. We have opcode and we have operand. Okay. So operand could be in memory, in register, or in part of the instructions. (24) Identify the operational instruction for LC3. There are 3 operational instructions in LC3. You have add, you have and you have not, right? We've used add, right, to be able to bring value to a certain register. We've used and to clear register. Okay. We also use it to copy. Actually, we use add to copy. Then we use not to set up the twos complement, right? So not will be the ones complement, and then we add the 1 to it to get the twos complement. So these are considered to be operational. Make sure you know all 3 of them, because there could be a question that asks you which one is not an operational instruction. Any question with 24? Okay, 25. Oops, sorry. Whiplash, second there. Okay, so what are the conditional codes for LC3? And we touched on this when we talked about branching, right? So you can have BRN, which is for negative, though that is one of the conditional code, right? We would branch when it is negative, if it is negative, right? We can have P for positive. We would branch if the value is positive, so it would check the line right before. We can have Z for 0. It would branch when it would be 0, and you can use them together or individually. It's used to indicate the condition in which the bit can be used by one of the control instructions to change the execution sequence. And that's what conditional statement is, right? It would change the execution sequence in your program. Question on 25. For 26, which instruction stores the content from the source register onto the memory location, allowing the instruction to access full memory address space? And that's your store indirect. Excuse me. It's STI. So the content of the source register is stored onto the memory location when you use STI. Then for 27, write the instructions to load address X3105 from the label add 1 onto register 1 without accessing the memory. Excuse me. So we would have an LEA, right? Load effective address, register 1, and their label is add 1, and then we would fill it. Any question with 27? So the key word for this is without accessing the memory. That will be your LEA. for 28. So have the expectation that you will see LC3 code on your test, right? Since I'm not having you write code for the final, you will be presented with snippet of program or the entire program, and you would need to determine what that program is outputting, or a certain line is equal to a certain value, and so on. So you have to know how to read LC3 for the final. So for 28, it asks you to write code to calculate z is equal to x minus y, for x is 9 and y is 5. And we practice a lot of this in our assignments and our lab already, right? So first thing, we gotta originate at hex 3000. And then I wanted to make sure that I declare my variable here. So we would fill them with address location. So X, I have it at 3100. Y is 3101. Excuse me. And Z is 3102. Then I load X to register 1. Load Y to register 2. Then I clear. Okay, so I clear R1 using AND. I add 9 in X because it's loaded. I clear register 2. I add 5. Okay. And then I negate Y. Set up 2 complement. So Y is now -5, which is in R2. Then I add them. So that way I would have X subtract Y. And what I want to do is I want to take the value in R1 and I wanted to store it to Z. And we can find the value when we run the program, and we would go to that location on our simulator and we would look for whatever is in Z. So it should have 9 minus 5, which gives you 4, right? And we store 4 out to Z. So our program, when you go to Z, which is at 3102, you should see 4. Okay. Any question with 28? Okay. No question. So it's very basic program, right? We've done more complex program. 29, describes systematic decomposition. And it is breaking down the problem into subtasks. It decomposes each subtask into smaller subtasks, and then even eventually smaller subtasks than the previous, until you get to the machine instruction level. Okay, so make sure we know the definition for systematic decomposition. Any question with 29? Okay, for 30, which LC3 instruction has no limitation on where the next instruction to be executed must reside, and that's jump, JMP. With jump, there's no limitation, right? You can just send it. So we would then jump to, right, a label. Okay. So if you try to jump to a register, it's going to throw an error, right? We only jump to a label, and that at that label, we would have additional instruction for whatever that we're trying to do. Okay. So jump for 30. For 31, given the opcode, identify the appropriate instruction. So you need to know what at the binary level, what add looks like. Okay. Let me pop this over. So what and looks like and what not looks like, and the other ones. Okay. So the chapters that we went over, right? Some of the exercise we've done, I've had you put in the binary equivalent for that opcode into the bit location. We've done that with add and not and so on. So you can go back to the notes and your assignments and you can look at those. For 31A, your opcode 0001, that's going to be AND. B, opcode 0101. I'm sorry, the first one, A, that's going to be add. 0101, that's going to be AND. Okay. For not, that's going to be 1001. And then your LDR 0110 and STI 1011. So make sure that we know our opcode. You will have questions on these on the final. For 32, oops, sorry. You would need to know your trap vector. We need to identify the appropriate trap vector. And we have quite a few areas where we talked about this in some of the earlier labs and also the later lab, and then in later on in our notes, the later chapter, right? When we talked about your system call and then with the trap, and then we talked about function call and returning from a function and so on. Okay, so in the later chapter we touch on that. So for in character input, that's vector 23. Whole execution, vector 25. That's B. For C, when you do puts, that's vector 22. Right string pointed to R0 on the screen, that will be a put. And for get character from keyboard, that's your get C, and that's vector 20. Any question on trap vector? Okay. So you might get a question that asks you, what is the pseudo instruction for trap vector 25? And you have to know that it's halt. Okay. Or what is the trap vector for in? Right? 23. And so on. And this is a little harder to remember sometimes because you don't directly use it. You see it with the simulator, right? But we have gone over specific ones and also more additional to this, right? Okay, any question? Okay, so this is part 1. I'm going to go to part 2 next. if we need to multiple characters inputted from getC, do we use getC as many times? Yep. Yes, Alex. That is right. And you need to be able to make sure that you put it somewhere and convert it, right? ASCII conversion is needed when you have input, and then before you output it, you got to convert it back. Okay, so lab 2, we touch on that, but yes, you can get multiple characters that way. Okay, so part 2, that's going to be 6 through 19, and then we have a third one, which is going to be for programming. Okay, so let's try to hit it all at one meeting. What is instruction in computing? And instruction simply is a fundamental unit of work. So question 1 for part 2, instruction is a fundamental unit of work. For question 2, identify 3 types of instructions. That will be computational instructions, and add, etc. 2, data movement instruction, load, store. 3, control instruction, jump, branch. Okay, so those are the 3 types of instructions: computational, data movement, and control. For number 3, create an assembly program that contains the following criteria. X is set location hex 3200, Y is set location hex 3201, X is equal to 4, and Y is equal to 3 times X. Okay, so you can make it simple, or you can make it with the multiplication function. So I went with the simple approach with addition for multiply. Origination at hex 3000 to start. Load X to register 1. Add 4 to register 1. So X is equal to 4. That's what it asked for here. Load Y to register 2. Clear. Right, I didn't clear X. You can clear X before you add 4. That's fine. So I clear register 2 because now it's Y. And then I have it added. Okay. So R1 added with R1, at that point we would have 2X, and that's going to be in Y. So Y is equal to 2X. And then I added it again to make it 3X, right? Because it's X plus X plus X. So we have 2X here in Y. And then Y again, we're going to add another X. So that's going to give us 3X. And then I copy to register 0, right? And I should comment here, need to ASCII convert before put. Okay. So I need to ASCII convert. I forgot that last time. So then if you wanted to output and show it, then you can ASCII convert and then do puts. But we can always go to the location to check our value, right? So if X is equal to 4, 3X should give us 12. So we can check at 3201 to see if we would have 3X there. Okay. But in any case, we would then halt, and then we would do a .n after we fill, because it asks us to fill. So 3201 is Y and 3200 is X. Easy program. Okay, any question? Okay. So like I said before, make sure we know how to read LC3 and write LC3. Next one. 4. Create assembly program using LC3 that contains the following criteria. A plus 4 is greater than B, given A at location 3100 and B at location 3101. So we would start with the origination address, originate at hex 3000. We load A to register 1. We add 4 to register 1 to make it A plus 4, right? Like what I mentioned before, when you're working with equation, you're going to work on one piece at a time. And if you have a parentheses, you have to start with that first from the inside out, okay? Because when we look at C programming or C++ programming, right, it's going to take precedence in the parentheses first. So and that's how you would mechanically move across or down the program by doing the same thing. So here we have A loaded. We add 4 to A. Then we load B. Now we're going to do this part. Okay. And then I did this a little bit differently where I subtracted, but you can branch it earlier. You can do the comparison right after you load B, right? And the way that we can check is if B is less than whatever's here, then we can branch. So what I did was I used algebra, and what I did was I subtract B and make it greater than 0. So I wanted to make it like this, right? For the branch. Okay. So what I did was then next line, I would have it 2 complement. So it's going to not register 2 at the 1. So now we have negative B. Then on the next one, I would then add them together, right? Because we would have A plus 4 minus B. So here is where we would have A plus 4 minus B. And we need to branch to check it where it would be greater than 0. So that's easy because we can branch it for positive. And so I would branch it to comp for compare. And if it's positive, then I just store to A, B, and then halt. And then I fill. And lastly, we would end. Okay. But you can approach it another way. So whichever way you wanted to do that, but systematically, we just got to make sure that we apply the condition. Excuse me. Any question with number 4 for part 2? These are super easy. We did this at the beginning, so. And you can look at the comment as well. Okay, so 5 is very easy. It asks you to look at your code and add the comment. Okay, so we use the semicolon to add our comment in LC3. So when we do an add, register, and then hex 0 or 0, decimal 0, it's simply a copy, right? When you add a 0 to anything, basically it doesn't change the value, and then you put it into the destination register. So it's going to take the content of register 0 and put it on register 3. So for 5A, that will be copy register 0 to register 3. Then for 5B, we're going to look at these lines. And remember, we talked about the offset for ASCII. So we would add R3, negative 16. So we subtract 16 round 1, we subtract 16 round 2, we subtract 16 again, round 3. That will give us negative 48 in decimal. And that's what we need to use for ASCII conversion. Or you saw the other technique in the example from the publisher, right? From the book, that it would be, we can fill it, right? We would fill it with the hex equivalent of negative 48 decimal. So for B, we subtract 16 from register 3, subtract it again, and then again. That means that we convert the values in register 3 from ASCII to hex by subtracting 48. And make sure that that's decimal, right? The hashtag tells us that it's decimal. Then in 5C, we have begin label. We have a load effective address, register 0 to prompt. We would prompt a string, enter the first number. Then we're gonna put, then we're gonna get C. Then we move, we copy from register 0 to register 1. So going back to the earlier question, right? You can get C many times, but we wanted to make sure that the value that it's obtained, it's going to put it onto a register and then convert it from those registers. Okay. So in the prompt, we have a string, enter the first number. So the first one is load effective address of prompt to register 0. Display on the console. Input character. So that means it's obtaining input. So it's waiting for the keyboard now, right? And then once it gets the input, we're gonna copy the content from register 0 to register 1. As you know that register 0 is used for these puts, get C, and so on, because it's the first one. Okay. So I just retyped the comment there below instead of each line. Any question for C5? So again, for D, we copy register from content from register 3 to register 1. And then after that, we would branch to show. So branch if 0, so it's going to check what's in register 1. If it's 0, it's going to send it to show. If it's not, it's going to continue to the next line. Yeah. So you would then going back to 5C, you would then have to move it, right? So it's going to come in register 0. You can put it into register 1, then the next one you put in register 2, and then you would then convert it. So if you're asking for a 2-digit value, but remember, recall that when we were doing like, so if you're asking the user, be careful with that. If you're asking the user to enter the number 22, right? So the first input is going to be a 2, and the second input is going to be another 2. Okay. Now you need to make sure that the computer sees it as 22, not 2 and another 2. Okay. So because 22 represents what? The first 2 is going to be 10-digit, right? And the second 2 is going to be a single unit digit. So you need to take the first 2 and make it a 20 and then add it with the second input, which is going to be 22. Tricky, tricky. Okay, so after you convert it, and make sure that we gotta represent it as like, 10-digit, 100-digit, 1,000-digit, and so on. So you have to logically think about that, because the input is input, but we want to represent it to how our human scale is going to be for 22, not a 2 and another 2. Okay. Yes. Yes. So you have to make sure that the first input is going to represent the 10, right? Multiple of 10. You got it. Okay. Any other questions? All right. Okay. 6 in LC3, what are opcodes? They are reserved symbol that corresponds to LC3 instructions, what the instruction is asking the computer to do. Okay. So opcodes are reserved symbols that correspond to instructions. And instruction, earlier we said that it's just a single unit of work, just task for the computer. Then for 7, in LC3, what can be considered operands? Okay, operands based on our notes, that will be who the computer is expected to do the opcode to. So it would use the opcode on the operands. And operands could be registers, right? Like you would have LDR, R1, R2, R1, or LDR, R1, R1, R2. Okay. Registers, which is specified by the register number. I should put not the N here, but this. Okay, where N is the register number. Let me change that back. Sorry for the confusion. And then that could be values, right? Numbers. Hash is going to be your decimal, and X is for hexadecimal. And those are the two that we're using mostly in our code. Label, which is symbolic name of memory location. Like we would give it a name where we would recognize, and that would be tied to a location in memory. Okay, so those are operands. So you would have opcode and operands. All right, for number 8, specify the purposes of the following opcodes. BLKW2, that will be block write 2. Allocate 2 words of storage, 2 times 16 bits. B, dot fill hex 3101. Allocate 1 word, initialize the value hex 3101. C, dot strings. This is a string. Allocate 13 plus 1 location, initialize with characters and null terminator. Why is it 13 characters? You count up the characters. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 plus 1 in the back. So any question with A, B, C? Okay, so this one we kind of touched on already earlier, right? The trap vector. There are additional vector that's listed here that wasn't on the other questions. So for 9, it asks you to identify the appropriate trap vector for the directives, and 100% sure that trap vector questions will be on your exam. So make sure that you look them over and go through the notes. So A halt is vector 25, B out is vector 21, puts is vector 22, in is vector 23, get C is vector 20. We saw those, some of those earlier. Okay. Any questions with 9? All right. What are the basic constructs of LC3 programming for question 10? So the basic constructs are sequential or conditional and iterative. So for sequential, instructions naturally flow from one to the next. No special instruction is needed to go from one sequential subtask to the next. It's just going to go flowing down. Okay. Conditional and iterative, that will be that you have to write code that converts the condition using branching with the condition negative, 0, or positive. Okay. So basic construct of LC3, it will flow naturally, right? Top to bottom, that will be sequential. It will go from one subtask to the next. Or we can apply condition or iterative using branch and with the condition negative, 0, or positive. Let me move this down to the next page so we can look at the other ones too. All right. For 11, identify the steps for debugging. First, we're going to examine the sequence of instructions that's being executed. Second, we're going to keep track of the results that's being produced. Third, we're going to compare the results in each instruction to the expected results. Okay, so make sure that we're familiar with the steps of debugging, and you can apply this in your project, right? Look at your sequence of instructions. So when you first learn programming, right, when you run into an error or any kind of problem, what happens? What does your instructor say? Or you would just look through your code, right, line by line. Okay, tedious but rewarding at the end. Okay, and then when you look through the line by line, you said, okay, what's happening in this line and what's happening here? And eventually you're going to find the area, right, that's going to be the problem. Then you're going to fix it. Now, a lot of if you use IDE, the debugger is going to point out like where the problem would be, which line, and then you will go to that. But you have to also look in that area, right? What's happening before and after, or when you run into a logical error. Okay. So as we track it, we would see, okay, what the kind of result am I getting there? And then we're going to look at, compare that to the instruction. And in assembly, it's important that you do these steps when you troubleshoot, when you debug. Okay. So that way you see what's happening. And in the simulator, it has the step over or step through, so you can look at line by line. Okay. For 12, using LC3 assembler, what type of files are generated in Windows system? And we see this every lab, right? Every Thursday when we do the lab, when you assemble your file, before you assemble it in assembly, you save your file as the assembly format, and it will be .asm. Okay. Doesn't matter if you write it in, right, Microsoft ASM, NASM, right, it's ASM. So for us, we saved it, right, and then we would use the LC3 simulator, or we use the editor to assemble it, and then we would use the simulator to look at it. So from the assembly language program, the code is in ASM. Then we would use the assembler to assemble our code. And the assembler would give us 5 type of files: binary listing, which is a .bin, hex listing, which is a .hex, object file, which is your OBJ, which is used to simulate, right? Symbol table. Remember when we talked at the last few chapters in the text and for our semester, we touch on symbol table, right? So symbol table.sim and listing files.list, LST. Now in some assembly language, you would see that, you know, when you link, you have to set up your link when you would need to, if you're using a certain library with C compiler, you need to link it properly. And then with that, what it would do is as you link it, it's going to update, right, what you see in LC3, that the, you know, like the symbol table, it needs to update that because you're pulling stuff from another module or another package. So it's going to update those, and as you assemble them, so it's in the back, it's still going to be very much the same. So once you learn LC3, you can, you know, it gives you the basics, so you would be able to write it. Like learning C, you'll be able to write C++. Okay. All right. Oops, I got too fast. Okay. 13, in LC3 program, what does the object file contain? It's the starting addresses and machine instructions. And that's why you need, when you load it in the simulator, it has where it's your program's going to start, right? And it's very mechanical in that we have to say origination here. Okay, and it's gonna start at that line. It's gonna go down, right? We talked about the sequential flow. Then 14, describe the loading and the linking in LC3 programming. Loading is the process of copying executable image into the memory. You would use sophisticated loader that's able to relocate image to fit into the available memory. So because it's dynamically allocating, right? So, you know, the way that it's presented in the textbook and in, you know, in a lot of the diagram that you see, it would be like sequential. So it's easy for you to view, but memory, the way that we design it, is just, it's gonna be fast writing, right? Dynamically allocated. So you can apply the loading process on more of the complex type of program. So, and then linking is the process of resolving symbols between independent object files. So like I said earlier, you would link to a package or a library, and with that, it updates your symbol table. Okay. So if you define a symbol in one module, you would then be able to use it in another. Okay. And if I know some of you took Java class with me, right? You can import in your own custom package and module in Python, that will be module. So at that point, when you issue the import statement, what happens is it's going to update your symbol table. So your compiler takes care of all of that, right? But for us in LC3 or in assembly, right, we have to put in the notation .external. Even if you use a C compiler to assemble your program in like other assembly language, you still have to specify, right, where that library is. It's not native to that particular system at that point, and or that program at that point, and then you have to be able to set a path for it and so on. So this is why you would then organize all your component of your program in one folder directory, right? So when you use like Visual Studio or an IDE, it starts out with creating that project folder, so that way it keeps everything together for you, right? And when you link stuff, it's going to link directly to that source folder. Okay, because in the back, what happens is it's doing the .external, and then it changes the symbol table and your files and so on. Okay, so here I talk about, and in the notes, the book, it talks about this too. I added that some notation, just that .external, is used to tell the assembler that the symbol is defined in a separate module, and the linker will search the symbol table of another module to resolve the symbols to complete your code generated before loading. This class is a gel in for all the other programming classes. If you understand stuff in this class, everything else in other languages makes so much sense. Why they're doing things in Java, like the way that you set up packages, why it's like this, why you're importing, why you're, so on. 15, what's the purpose of control status register? So CPU tells the device what to do, right? So it write to control register, and then CPU would check whether the task is done. It would read the status register. Okay, so if it wants the device to do something, and device like input output device, we talked about that, right? Screen, keyboard, at the simplest level. So if it wants something to do, then it would write to the specified register, right? Keyboard has its own register, and the display has its own register. And then if it wants to see if it's done, then it checks it and read the status register. For the polling in ISA input output management, it keeps checking the status register until the new data arrives or if the device is ready for the next data, right? Are we there yet? Are we there yet? Okay. So it checks the status register until the data arrives or if the device is ready for the next data. Any question with 15, 16? For 17, it asks you to describe interrupts for I/O, and the device sends the signal to CPU when the data arrives or if it's ready for the next data. The CPU would it's regularly performing other tasks instead of polling devices, right? So it's doing something else. It's kind of like the busy parent, right? So if the kid needs the attention or the busy teacher in the class, and if the student needs attention, that student would then raise their hand. That means sends an interrupt and say, hey, I need your help. So, and the book uses the phrase wake me when we get there. Okay, so interrupt me when you need help. So that will be interrupt. Question on these? I'll move this down because it's lengthy. So, all right. Next question. What are the memory address assignments for keyboard data register and keyboard status register, your KBSR? So keyboard data register, KBDR, that's assigned hex FE02. So the data is 02, and then the keyboard status register is assigned hex FE00. So make sure we know these. Likely you will see them on the test. For 19, describe a stack. It is an abstract data type, which is a storage mechanism defined by the operations performed on it, but doesn't have to be a specific manner in which it is implemented. And it grows downward, last in, first out. So as it adds in, right, more, then it's going to push it down. So it grows downward. So make sure we know what a stack is. For 20, identify the operation to add or remove an item onto a stack. We would add an item by doing a push. So you add an item onto a stack when using push. So we push an element onto the stack, okay? And then we will pop to remove an item from a stack. So you pop. So we covered these in our assignments already, right? Recently too. 21, describe a supervisor stack. It is a region of memory used as the stack for internal service routines. LC3 save the state information to the special stack. And this is a supervisor stack that's used only by the programs that's executed in the privileged mode. Okay, any question? And when you take operating system classes for computer science, they will touch on like the different type of mode, right? And because in OS you see that, you see the mode for when it's privileged mode, or they call it, system mode, where it's only accessing a certain part of the region. And then you got the user mode, where that would be something that would be adjustable, that would be used with, specified by the programmer. Um, and so here you would see it as the background in how we would look at that. So your supervisor stack is a protected area of your memory. Okay. A lot of books and that talks about OS, it talks about, system protected or protected memory. All right, 22. What does the activation record bookkeeping contain? We talked about return value, which is space for the return value, returned by the function allocated, even if the function it doesn't need to return anything. Return address, that will be say pointer to the next instruction in calling function. It would be stored in R7 in case another function is called using JSR. Dynamic link, caller's frame pointer used to pop this activation record from the stack. So that will be caller's frame pointer. And it's used for activation record. For 23, when do you save and restore registers? If you know that the values would be destroyed by the service routine, then we need to, or when we need to use the value later on in our program for other things. Okay, after that action. Any question? So I had a student from Denmark contacting me today because he was watching your CIS-11 video for this class. And he said that he's taking the classes over there like this. So as you see, right, computer science is computer science. So interesting enough that they're teaching LC3 in Denmark as well. And I've seen lecture notes from like other parts of the world for LC3. It's pretty interesting. All right, 24. What is a stack pointer? It consists of sequence of memory locations along with mechanism. Stack pointer keeps track of the top of the stack. Remember how we looked at the example in the presentation? It uses R6, right? Register 6. So it's a location that contains the most recent element push. So it's using that to see if the element is there, if it's pushed on, right? And then we can also use it, like I said, some meter. So we would also use it to say, oh, that's the location of the push element. And we would use that location to pop it off. The top, that will give us the top. Okay. So it's a sequence of memory location along with the mechanism. to keep track of the top of the stack, the location containing the most recently pushed element. Okay, any question on these? We went over them already in our assignments, so expect them to be on your final. Okay. So 25, what occurs when there are too many items being pushed onto the stack? You would have overflow. And then if you have too few, right, underflow. What causes the interrupt-driven I/O? So it is an unscripted subroutine call. It's triggered by an external event. And that could be device signals that needs to be serviced. Okay. Processor save states that start service routine, or when finished, the processor restores the state and resumes the program. So an interrupt driven input output it's just a not scripted subroutine call, right? That's happening outside of that. So when it receives the signal from the outside that needs to be serviced, like analogy would be you got the teacher that's busy, the students that needs help, and then there's somebody from the outside running into the classroom and said, wait, stop, like I have an emergency, right? So you have an external event that occurs that generates the interrupt as well. So that's going to generate the signal that will trigger it. 27, why would you use a stack? Because you have limited registers, and in LC3 we have 0 through 7. Oh, thank you. Oh, thank you. Yeah, I use some Cal State San Bernardino material too. So this, but they teach MIPS book, not this book. So I stuck with the original book. Anyway, thank you. All right. For why do you use a stack if we have limited registers? If we have, it would be for conveniently calling the convention for subroutine, right? You saw how our later lab that we have the stack, and then that would be applied with the subroutine, and also algorithm that naturally express last in first out data structure. So if you want to implement data structure, like in the sense of C++, if you think about like vector, that's, you know, that's a storage that you push and pop, and it pops by default at the end. So but we talked about like how that would have a we would use pointer in a singly linked list, or doubly linked list, you know, in deck, stuff like that. So if you want to make it more advanced with data structure and assembly, you would consider implementing stack and subroutines that appropriately, you know, apply with the algorithm of your program. Okay, the program is really designed by its programmer. So, you know, you wanted to make it nice and have data structure, then you can consider adding the stack. Okay. All right, 28. If you use base address hex31A0 as a base address to allocate a word for each of the element, what is the address of the 10th element of the array? And we lastly touched on this right before we took a little short break. So you would have the hex 31A0 plus 10, which is the A, that will be hex 31AA. And then for 29, if you use a base address that is hex 31F0 to allocate double words, the keyword there is double word, right? For each of the element, what is the address of the 7th element in the array? Okay, so if we start with F0 and we have a double word, so you would take 7 times 2, which gives you 14, or E, so you would end up with hex 31FE for the 7th element in that array, if it's double word. Okay, so make sure we know these, right? They are going to be on your test. Not exactly like this, of course, but just know how to calculate them. Okay, how can you use pointer to obtain multiple results throughout the program? Use arguments in the results. We would pass the address of the variable where you want the result to store, which is useful when you have multiple results. And the return value is going to be pointed, so the return status code is the function result. (31) What is recursive function? And is one that calls itself. So it is one that solves its task by calling itself in smaller pieces of data. And the perfect example for that is factorial functions, Fibonacci, right? Running sum, and so on. So as we didn't have the last quiz, right? So you would see some of the later questions showing up on the test, or close to it anyway. That's why I put them in your review. For 33, in C programming, what is the purpose of a data structure? It allows you to group related items together. We talked about struct in C or C++. We would be able to organize data in a way that it will be convenient and efficient for execution. And then the array is a one kind of data structure at the simplest level. And I know some of you took CIS-17C or currently in it, right? And in that class you use data structure. You in Python, you don't see a big drive behind that, right? Like you can implement like deck and things like that with Python, but you gotta bring in the module, right? The library for it. And same thing with C++. You can bring in the STL for it and be able to use it. But because you have dictionary incorporated with Python already, so it's naturally able to scale for, that. So in Python, we mainly use dictionary for most part. Right? I just went over some stuff with my network Python class. And when we looked at like when we automate some of the tools with cloud, like the majority of it is pulling from the dictionary and into JSON, and then you would be then importing in the JSON file and then converting it. So pretty interesting. For 34, in C programming, what is a struct? It's a mechanism for grouping together related data items, but different types. Like we talked about int, right? That would be different than char. and you might want to group them together for your program. So you would use struct. Okay. Any questions on this? Okay. Everything we covered already. So this is just a review, right? Example of that. We saw that. 35. A linked list in C programming is an ordered collection of nodes which contains some data connected using pointer. Okay. So if you wanted to do well in 17C, right, you have to start with a solid knowledge, knowing how to use pointer, because that's basically take care of the rest of the class. Because if you can write tree, you can write different data container using pointer. 36, what are the advantages of using linked lists in C? Dynamic in size, it can grow. Okay. Easy to add nodes as needed, right? Remember the last one, we got to terminate it, right? But on the, in this, the time that this book was written and the material was put together, right? They didn't really expand on C++ doubly linked lists. On C++, you can loop it back and point it back to the first node, which allows you to have a non-ending list. Okay. So you would make it easy to add the node. You can also remove it, the n, or, you know, if you have removed the n, you gotta say the previous one as the n. Otherwise, it doesn't know the n if you're using singly linked lists. But you can remove it in the middle. You just disconnect that pointer and then point it to the new the new one. So you just basically associating memory, and that's what all programming is about. Okay. All right, questions? Okay, so I think I can do the third part, so hang tight. Do you have any question for part 2? Okay, let me stop share. Let me go and open my last one. Let's see. I don't have the file for some reason. I don't know what happened. I might have deleted it. Okay, give me a minute and then I promise. If not, I'll actually post it. But I want to give you a chance to ask questions. Maybe I'll post it for you because I gotta go look for my file. I don't know. I'm a little bit unorganized today. I don't know why. Okay. But anyway, I don't want to hold you a lot longer. So looking at, I have the student version. I don't know what I did with my old one. Okay. Okay. So this part is about the programming part. Okay. This one is super easy. If you did the exercise that we just went over with the LEA display string, right? In part 2, it already show you, how to do that. So you can also write that. Okay, by this point, you should be able to write this on your own. For number 2, this one is going to take 2 input for the decimal, right? So we're going to do a get C, move it, and then a get C, display sum. And then for part 3, for exercise 3, when we work with the equation, remember we just got to load the label from the locations, right? And this one is just like the XYZ one that we just done. So super simple with that one too. Okay, not even that much in the code. And then we did a similar one earlier with the x plus 4 is equal to y, right? Or we branch it. So in this one, it's greater than 0. So you load the label for x and y, then you add them together, or you subtract, make sure that we negate x. So you 2 complement x, add them together. Then you check for branch. So if it's positive, right, then you're going to send it to this part, right? So if I say if pos, we're going to send it to Z section, right? Z label. And then from there, we would load Z, and then we have to add it to Y. I'm sorry, to add it to Y to a register and then store it to Z. Okay. And then if it's not, if it's negative, I'm sorry, if it's negative or 0, then you're going to send it to this section where it's going to do Y minus 3. Okay, so this one is a little harder than the other ones, but it teaches you how to use branch. Okay, so let me find my stuff. I think I have it on one of the drives that I have, and then I will post it up tonight. Okay, for the third part only. And then for the students who missed the first 2, they can watch the video. Okay, would that be helpful if I post it, or you don't care if I post it or not? Okay, let me see. 1 second. Let me double check, okay? Okay, so there are 3 parts. Okay, so let's clear this up before we end. Part 1 we went over, part 2 we went over. So I will put both of the same video on the pages so that way people don't get confused. They just have to watch the second part of the video for part 2. This is the one that I'm talking about here, assembly programming final review. Yeah. Oh, you're right. Let me check the file. Yeah, this is what I'm talking about, right? Yeah, it's this file. You're exactly right. So you're supposed to write the LC3 program, right? You can write it in the editor and then screenshot it for me, or you can write it directly onto the actual document itself, like what I've been doing. Okay. What I'll do is I want to make sure that I will tell you the location now. I can post it in there, but sometimes people don't look after they download the file. So I will put the video for today here, and then I will change this page to the actual answer key for this one. Okay, and I will rename it. I would say, assembly programming final review answer key or solution or something like that. So you can find that there. Okay, so if you're stuck, but I encourage you to do it first. If you are stuck, then you can go here, and then so that will address some of the questions that you have for your project, like how do I get to input for this project. Okay, so I will post that there. Okay. Oh, so sad. last session that you're gonna have with me live, but you did it. You made it all the way to the end. Assembly is not for the easy. um, but I'm happy that you got a lot out of this class. We learned together, we programmed together, and um, I hope that you will further explore it. You as you see that ARM job is very highly demanded. So if you're able to do assembly and you enjoy it, many of my students after taking this class, they went on, they learned, ARM and other languages, and they pursued the job in the field for it. So it's not for the common. So a lot of people can do C++, Python, Java, you know, you name it, but not a lot of people can do this. So if you like this can be for you. Right. It is not as easy as another class in programming. Um, and when I first taught this class in Microsoft ASM, though, I have to say that I started with 20 something and I ended up with 11, so 50% drop. So I replan and I use LC3, which works out a little better, and students are understanding it. And you will see, so this class now transfer at Cal State San Bernardino. Before it didn't, but now it's transferred. I just talked to the counselor and the student who just transferred there. Um, and then there's another class after this class for the upper division. Expected you to know the content for this class. So be prepared that you're going to have the next class that's going to continue from this in the upper division for computer science in whether UCR or Cal State and so on. But, let me stop recording. And so